So this is our third lecture in vapor power cycles, and we started with the Carnot vapor power cycle. It shows us a lot, it teaches us a lot, and as we move into the Rankine power cycle, we'll see changes or adaptations or enhancement features of that cycle, and it can all kind of go back to some simple things. That heat addition, you really, if you're going to bring heat into a heat engine, and you're trying to produce or convert as much of that heat in to work out, you want to bring in that heat at high temperature. As much of it as possible at the highest possible temperature. And if you want to, you're going to have to reject some heat. But whatever you do, if you reject the heat, reject it at low temperature. This one's relatively easy, basically. Let's get a cold day, but we're stuck with dumping it to the atmosphere. And so typically get lake water, ocean water, river water, or dump it to air through some sort of chilling system or cooling tower system. And it's not much in that. But the other one, how you can bring in heat at high temperatures, is a theme that's repeated. And this is where a lot of innovation and adaptation or whatever of the cycle comes in. So it's a little harder, more opportunity there. Last time I talked about bringing in heat at high temperature, and then the one easy way is to increase the boiler pressure. True? Increasing the boiler pressure increases the temperature at which you're bringing in heat into the working fluid. This has been known for a long time. And started the Industrial Revolution was burning something to turn something. They burned something to boil water, use that steam to turn something. Steam engines and steam, this and that. Well, there's a lot of people have died from boiler explosions. This one here is the worst United States maritime accident ever. And so it was at the end of the Civil War, April 27, 1865. There was a ship on the Mississippi. I forget what did it leave. Did it leave Memphis? It was transporting troops home up north, and it blew up in the middle of the night, and it was absolutely loaded with people. I don't know if this is a picture on the day or the picture the day before it was took off. But of the passengers, it should have had maybe less than 400 passengers. It had over 2,400 passengers. A lot of them were soldiers who had been in prisoner of war camps, who had been released. And the Union, or the government at the time, was paying these private companies to help transport rail and boat soldiers home. And there was a lot of money to be made if you had something that float and you could load it up with people. And that boat probably should have been put down for service or inspection. But anyway, when you put a lot of people on it, then you're trying to go upriver, heavily loaded, what's the engineer going to do that's operating? Is going to throw the coals to it, stoke it up, and boost the pressure. And that steam boiler exploded. Now, this is interesting in the sense that there's some conspiracies that it was a Confederate saboteur. So you can watch a movie on this and some other stuff. But it was a huge loss of life. They don't know exactly how many people, because they really didn't have exact records of how many people were on there. There was about 200 civilians, non-U.S. Or non-prisoners of war going home, non-soldiers. But there was just under 2,000 dead in a big tragedy. And when it blows like that, you're out in the middle of the river and it's midnight or 3 a.m. It's a huge loss of life. So, the American Society of Mechanical Engineers, which hopefully everybody's familiar with, was founded in 1880. It was founded on trying to have common things for communication and building, machining things, and they started having formal meetings, and they would on work practices, how to make things and how to make them more uniform. Well, in 1880, there had been a lot of steam boiler explosions, and in 1884, the group established the boiler testing code. This is straight off the ASME website. And really, ASME is has been a long time known for its boiler code, boiler and pressure vessel code right here. What happens is these codes are put out by experts in the field, mechanical engineers. They're not put out by government bureaucrats. And then what happens is the state laws, their state governments, adopt those and turn them into law. And so once the code has been adopted in a few states, then it has a large ripple effect and gets adopted in many, many states throughout the United States and its territories and Canadian provinces and different parts of the world. This was, even though they had early 1884, they really stepped it up after a Grover shoe factory disaster in Brockton, Mass. In 1905. I mean, they would have boiler explosions throughout the United States, a few per week. And often there was a loss of life at each one of these boiler explosions. But let me see if I can pull up the Grover shoe factory. So there's a picture of it before the disaster, and here's a picture of the site after. So you can see it was just devastated the building. And it happened in the morning. I think it was before a lot of workers were there, but enough workers were there. It was a very wooden structure, a lot of things which were flammable, and also some natural gas or gas lines in there. So once the boiler exploded, then you had other sources, and it turned into a big fireball. And a lot of people died. 58 people died. And here's the picture of the boiler as it landed in some Miss Mary Pratt's yard or in her home. That's the boiler. So there's another one that I'd like to show you. Oh, actually, if you wanted to, you can find a lot about the Sultana disaster on YouTube. I think there's a PBS documentary, especially honing in on, was it Confederate saboteur or just a simple boiler pushed to the limits and then exploded. There was one that I was going to show you. Here is it. Well, I have another one here. This is a video clip of a tractor being brought to county fair somewhere, or state fair. And it's a boiler right there. They're boiling water. They're burning to boil water. And then that tractor in 2001 exploded at Ohio. And so 5 people lost their life. Now, a lot of times what will happen in these antique tractors is they won't be able to get it back to the safety features even when they built it. So they'll, weld something tight that's not supposed to be welded. It's actually supposed to be able to pop out or blow out. And the operator may not be as skilled. You can find reports on this explosion, detailed by engineers, and why and how it happened. Tennessee boiler explosion 2007, and it has a surveillance video on it. Let me see if I can go to YouTube. Professor, this is the most exciting part of your lecture. Just show us YouTube clips. All right. No. Surveillance video. And we'll watch this one. So it's a fire tube boiler explosion. This worker, he's about ready to go to lunch. Hurry up, buddy. Yo-ho, it's time to go to lunch. That boiler right behind you. He looked at the clock and he is out of there in the nick of time. There was no loss of life. There's the explosion. And of course, some news video surveillance, I think, is going to come on. It's only a 1:17 video. And there's a side view of the factory, the plant. That was thwarted. The safety feature had been disabled. Oh, there's a lot of engineers went and found out why that happened. Yeah, it had been manually overridden. And then, so here's some pictures of it blowing. Let me see. The destruction. Stop right there. That's that's the lid on the end of the boiler. I couldn't pick it up. That's where it ended. The other end was shooting through the factory and went elsewhere. But I've read the report on this. Shattered windows in the parking lot, vehicles covered dust, blown over tree. Oh yeah, if you buy their steam generator, that wouldn't happen. All right, let's jump back here. So when you can, increase the boiler pressure. That's good. You're able to bring in more heat at higher temperature. What's the caution? You'll see it often. Metallurgical limits. And you have steam at high pressure. It's dangerous. It's been dangerous, and people have known that. Decrease the condenser pressure. Well, you have to reject the heat to the atmosphere. So although it's good, you keep it as low as possible, but you have to reject heat to whatever the atmosphere temperature is. What's the next feature to improve performance is superheat. Superheat. So on our temperature entropy diagram, we had stopped putting in heat when it becomes saturated vapor. There's a practical concern. When you expand it, even through the best turbine, you get kind of a low quality steam. So 20% or 30% will be in the liquid state, meaning liquid droplets rushing with the vapor. And that's bad on performance for your steam turbine. So what you do is you continue that high pressure and you superheat. If you superheated it and then expanded it, then it would be better on the turbine. So from a practical point of view, it's good for the turbine. Increases the steam quality at the turbine exit, so no little water droplets. And it's good because you're adding more heat at higher temperatures. That's good. Caution, there's even more of a potential for metallurgical failure and explosion. And then the next one is if you really have a limit, like don't go beyond here, no. Well, then bring it up so far and then expand it, but maybe expand it and then stop the expansion and at an intermediate pressure, reheat it back up and then expand again. That's called reheat. So you can see some of the enhancements already, superheat and reheat, to bring in more heat at high temperatures into the working fluid. So the superheat, as we just described, I won't resketch the temperature entropy diagram. What I did here was I made some calculations of what is the effect of the boiler exit temperature. This is thinking about superheating it in this direction. Now, there's a bunch of cases. One is if I have a 10 megapascal, 8 megapascal, or 6 megapascal boiler pressure. Well, if it's a 6 megapascal boiler pressure, right here is the temperature that it's saturated vapor, or the saturation temperature. And then beyond this, you're able to superheat it. At 8 megapascal, it's just under 300, around 295. We've solved that a couple times, or used that number a couple times. Degrees C, that'd be saturated condition. And then this is superheating it for the 8 megapascal. And likewise, you have a higher saturation temperature for the 10 megapascal, and then you superheat it. Well, you can tell it's better to go with higher boiler pressure. Look at the increase in thermal efficiency. And then go ahead and superheat. All of the lines are increasing. Voila, better for performance. Higher thermal efficiency. You can do the same thing playing with the condenser pressure. Make the condenser pressure low. This is the 10 kilopascal, 20 kilopascal, 40 kilopascal, all for one boiler pressure. And you can see that it improves the thermal efficiency, but you're usually stuck. What is the temperature of the lake or the river that you're going to dump the heat to? And then reheat. Reheat, you have 2 turbine stages. Let me do this. I have a problem right here. Let me work through this problem. So I'll read it first. Water is the working fluid of an ideal Rankine vapor power cycle. Superheated vapor enters the first turbine at 8 megapascal and 440 degrees C, and then exits at 1 megapascal. So you're going to have 8 megapascal, 1 megapascal. It's then reheated and then enters the second turbine. So you have a first turbine and then the second turbine. And saturated liquid enters the pump at a pressure of 20 kilopascal. So you have 3 pressures now, not just high and low. You have an intermediate pressure in which it's reheated and then put through a second turbine. So make a sketch of the plant. We're going to have basically a steam generator or boiler. We're going to come out and we're going to go through a turbine. Now, before we go to the second turbine right here, we're going to divert some of that, all of the steam actually, back to the steam generator for reheat. See that? They're going to go back to the steam generator for reheat. Then come over and go into the second turbine. That's really the only big enhancement now of this cycle. You then go into the condenser, and then you go into the pump, and then into the steam generator again. But this steam generator, it goes here. It's like the first pass through the steam generator, and then the reheat's another pass through the steam generator. So let's go ahead and label some states on our sketch. Maybe what comes out of the steam generator and goes into the first turbine is state 1. What comes out of the first turbine going back to the steam generator, state 2. State 3 is after the steam generator reheat. So this right here is reheat. And then state 4 here, state 5, and state 6. All right? Once I have a sketch of the plant layout, what I want to do is I want to make a sketch of the temperature entropy diagram. So go ahead and put just a bell-shaped temperature entropy diagram like this. And what I'd like you to do is, while I walk around the room, fill that temperature entropy diagram in. And here's a big hint to start off. How many unique pressures are there in this system? Is there only the condenser pressure and the boiler pressure? Or is there only 2? Or are there more pressures? And that'll help guide you. So put all 6 states on a temperature entropy diagram. So a lot of people have done pretty well. What I'll do is I'll say that we have 3 pressures. That the way to attack this is take the hint that I gave you. There's 3 unique pressures. There's the boiler pressure at what? 8 MPa. The reheat pressure, 1 MPa. And the condenser pressure, 20 kPa. So why not go ahead and draw a line of, let's say, 20 kPa, 1 MPa, and 8 MPa. So 8 megapascal, 1 megapascal, and 20 kilopascal. True? And state 1 is out here at what temperature? 440? And if we expand down to 1 megapascal through the turbine, that's from state 1 to state 2. It'll slightly go inside the dome. Usually you want it a little inside the dome. And then where is state 3? You got to go way back up here to the 440. I didn't draw this diagram too well, did I? State 3 is at that same temperature, 440. And then we expand down, maybe that's state 4, slightly around saturated vapor. And then we condense it, coming out of the condenser. And then a gross exaggeration, but there's really state 6, and those lines are terrible right there. They're really, really tight together. But there's state 6. It's straight up and down. 6. Okay? What is the temperature difference between state 5 and state 6? About a big half or a 1 degree C. All right? What would be the temperature of 20 kilopascal, the saturation temperature right in this vicinity? What's the saturation pressure of steam at 20 kilopascal? Yes. At 20 kilopascal, that's the pressure. What is the saturation temperature? Does anybody remember that? Or look it up, please. That'd be good. Tsat at 20 kilopascal. So it's right around 60 degrees C. At 8 MPa, what does it boil at? At 8 megapascal, which is 80 bar. What does the water boil at? Yeah, that's right. So it's right around 300. It's at 295 degrees C. So it's really gross exaggeration. We put state 6, 1 degree at the most. Degree C higher than state 5. And yet way over here is 295. And then way up here is 440. I'm not drawing this well to scale, am I? Right? All right. So make sure that you can do the layout. So this is the pass through the steam generator. And this is a pass through the steam generator. So the working fluid is receiving heat here as well as receiving heat there. Don't forget that when you compute the thermal efficiencies, etc. And then we know where the pressures and everything are, and we had the sketch. And here is a better temperature entropy diagram. So let's do this. Here is around 440. Horizontal line at 440. Here's a line at 8 megapascal coming down. So right there is state 1, isn't it? Now we go to 1 megapascal. We got to come all the way down. We're going to do isentropic expansion. There's state 2. This is all drawn to scale now, thankfully for that software RefProp. Then we reheat up to state 3. Then we expand down to 20. Here's the line of 20 kilopascal. Expand down to there. That would be state 4. Over here to state 5. And might as well just put 6 right there too. All those lines, the 10, 20, and 8 megapascal and all that lines are tucked in down there. Okay? All right. Then you make a table of properties, true? And that table of properties is, make sure and put like pressure, temperature. I like to put them in a standard list. Temperature, pressure, quality, specific volume. We don't need U, internal energy, so skip that one. H and S, and if you wanted to do flow exergy, that's fine as well. And what fixes state 1? Knowing the pressure and temperature. That pressure, that temperature, get the rest of the properties. How about state 2? I'm not rushing you through this, hopefully. State 2 was isentropic expansion through the turbine. So this S comes down, and pressure and entropy fix state 2, get the rest of the properties, especially enthalpy. Then we reheat, so pressure and temperature. Notice that we're at 1 MPa now, or 1,000 kilopascal. And we back up to 440, so we get the pressures, we get the properties. All right. Then we isentropically expand through the turbine from 3 to 4. Pressure and entropy, fixed state 4, same S. Then it's saturated liquid coming out of the condenser at that 20 kilopascal pressure. We put it through the pump. Now, you can sometimes use this S and you can get the P and S as long as that pressure is in the table for compressed liquids. Otherwise, you just say, I'm going to use VDP to get the enthalpy. So this enthalpy right here, that H after the pump, that would be 6, is equal to H before the pump, plus the specific volume of the liquid coming into the pump, times the pressure going out minus the pressure going in, and that's assuming isentropic work. You know, it's the minimum work. All right. So let me just repeat that. Sometimes you can use the compressed liquid table. Sometimes you can't. Just use the approximation VDP for the work. Okay. And then 7, what do I show right here? This is kind of interesting. What's that? 7? It's in the middle of that steam generator. Yep, that's right. It's right in the middle of the steam generator. What I'm trying to show is that you come in at about what temperature is state 6? Around 60 degrees. It's going to go out. State 1, 8 megapascal. What temperature? 440. And there's 3 phases you can think of. It's going to first have to get up to 295 degrees C. Then it'll be saturated liquid at 295. Then it'll go out at 295, get to 295 saturated vapor. And then from 295 saturated vapor up, it will be superheating. So 295. So you can think of right in here is that you're basically getting the temperature greater than Tsat. Here is you're getting the temperature up to Tsat. So you're heating liquid. You're boiling from saturated liquid to saturated vapor, and then you're superheating, right? So 7 was just an extra state thrown in there, and it's saturated liquid. And you can get the properties at that pressure, the enthalpy. Okay, because what I did over here was I said, how much heat comes into the fluid in that first pass through the boiler or steam generator? You'll see that I call it QB and then I call SG for steam generator. Sorry about that. I'm kind of mixing it up, right? All right. You can see that this many kilojoules per kilogram are just to take it from state 6 to state 7. No boiling yet. Just heating up the feed water, basically. Then you go from 7 to 1, which is both phase change as well as superheat, and 35% of the total heat that you have to put in there is just to get the water up to 295. Is that a significant fraction of the amount of heat added in that pass? Sure it is. That's a lot. And right away, that's a good lead-in to the next strategy for improving the performance of the cycle. Because what did we want from Carnot? All the heat brought in at as high temperature as possible. This amount of heating is, I would just say, wasteful from an exergy point of view or second law point of view. And you look around and you try and figure out a way to improve it. Okay, and that's going to be our last improvement. But before we go to that, let me just finish this up. You can calculate the work in the pump. You can calculate the amount of reheat right here. What is this? Oh, that's the turbine. First turbine stage, reheat. Second turbine stage. How much heat is thrown away in the condenser? We have one pump. How much energy to pump to boost the pressure? And then we're busting out the 2 amounts of heat in that boiler. If you add them together, this is the amount right here. And then we have work net and Q net. Always check that these are the same, right? in your calculations. If they don't balance, look for an error. And then we can make some calculations like what is the back work ratio, 0.6%. So right here, this is answered for the back work ratio, part D. The thermal efficiency, part C. The work developed by the turbine, well, you're going to have two of them. You're going to have nearly 500, then nearly 850. Add those together, and that'll be out of the turbine. And for the pump, 8.1 kilojoule per kilogram. And then the heat transfer in the boiler. In the boiler, we have nearly 3,000 right here. And then in the condenser is right here, 2252 kilojoules per kilogram. All right, so we're able to calculate the answers to all of those parts. But the last efficiency, or one of the last, is regeneration, and we're going to talk about that next time. But at this point, I want to leave you with the condenser. What you want to do in the condenser is condense it all the way, such that the pump gets liquid. You want to superheat in the steam generator. Even if you only have one turbine stage, it's helpful such that the quality of the steam entering, or the last turbine stage, is high. You don't want water droplets in your steam turbine. And then you can reheat between turbine stages, meaning you have an intermediate pressure, high pressure, intermediate pressure, and then low pressure. Now you have three pressures. That's the third pressure with reheat. And then we're going to move to regeneration. The purpose of regeneration is to increase that feed water temperature that's entering the steam generator. With this prior system, if we just stay with our 20 kilopascal condenser pressure, it's coming in around 60 degrees C. And there's a whole lot of heat just to warm it up, even before it starts boiling. And the strategy is to get that without using the valuable coal fuel source or natural gas fuel source or whatever fuel source you're using to burn, to do that. And so you look at getting a heat source within the cycle, sort of getting it where the steam is still hot, but it's not high, doesn't have a high exergy value, but it still has a high temperature value. All right, with that, we're done for today. Thank you for your attention.